Alrighty, guys. So where does all this energy come from in these chemical reactions? Well, it varies from reaction to reaction, but the simplest way to think about this process is that in order to go from the reactants side of an equation over here to the products side of the equation, it's going to involve some breaking and making of bonds. So keep in mind that if we start with something like CH4 and 2O2, that's very pretty to look at as far as formulas are concerned, but in reality, if we know the Lewis dot structures of these guys, we know that CH4 looks like this guy here, and O2 looks like this guy over here, and there's two of them, which is why there's two O2. So there's an O2 there, and there's another O2 there. So there's our two O2. So again, this is CH4 plus 2O2. That's really what's going on. Now what we're trying to get to over in the process is this guy over here. We're trying to get to a carbon dioxide and two waters. So again, that's what's happening in our equation. CH4 and 2O2 is trying to end up as a carbon dioxide and two waters. So this is where the atoms are starting. The carbon is bonded to 4 oxygens, and then 2 sets of 2 oxygens are together. But by the time we're all done, it's going to end up down here where the carbon is bonded to 2 oxygens here, and each oxygen is now bonded to 2 hydrogens. Well, how do we get from to here from this guy over here? Well, the first thing that has to happen is that all of these bonds essentially have to break. We have to rip all of these molecules apart. So we have to go here and we have to rip it into an individual carbon, 4 individual hydrogens and 4 individual oxygens. We have to rip this whole thing apart. We have to tear it apart. And then once we rip it apart and turn it into its individual atoms, then we can rearrange it and say, okay, now we want this carbon to go here with this oxygen and this oxygen. We want this oxygen to go with this hydrogen here and this oxygen to go with this hydrogen here. We can put these puzzle pieces back together again in order to make these two guys over here. So what it involves is the breaking and the making of bonds. So the first thing that has to happen is that all of these bonds over here have to be broken. We have to break all of those bonds. That's the first step. And then, once we rearrange everything, we get to make all of these new bonds over here. So, breaking and making bonds are endo and exothermic, as the case may be. Breaking bonds requires energy. In order to break something, you have to slam it with some energy. So if I want to break these bonds that are in this molecule here, I've got to put energy into this bond in order to grab onto it and snap it. So breaking bonds takes energy in. It is endothermic, or it is always positive for the delta H in order to break the bonds. Well, then that's pretty obvious, but it implies the other way around as well, that if it requires energy in to break a bond, then when you make a bond, you get energy back out of the system. So to go from here over to here, to put all these guys together, if we're making new bonds, then that is giving out energy, or that is going to be a negative number, or it's going to be an exothermic process. So if we put everything together and we compare the amount of energy it requires to break the bonds and compare it to the amount of energy that we get back for making the bonds, and we compare those two numbers, what we end up then with is an overall scale where we can figure out, all right, well, if it took this much energy here to break the bonds, and I'm going to get this much energy back out of it for making the bonds, well, that's negative and that's positive here, then the only real difference or the only real change in what's going on is the amount of energy from here to here, or the overall change from where you started to where you ended as far as their total bond energies are concerned. So, in order to do that, all we have to do is know and be able to look up, hey, how much energy is one of these bonds here? How much is it going to require for me to snap that bond? And then I just do that 4 times. How much energy is it going to require for me to snap this double bond? Do I have a number for that? Can I just look that number up, right? And then what am I going to get over here? Oh, there's a different double bond over here for carbon dioxide. Can I look up that number and this number and so forth and so on? And all you have to do is be able to look up those values. Now I've got a chart here, and this chart here is approximate bond energies. You'll find slightly different numbers in slightly different publications. So, like for instance, this 436, you might find it as 432. Don't sweat it. Just use whatever number they give you. You don't have to memorize anything or anything like that. These are approximate values. And everything that you see here in this chart is for a single bond. Double and triple bonds are far rarer than single bonds, so there are fewer of them to list. Here are some double bonds for carbon and carbon, for example. Here's a carbon-oxygen double bond. So again, these guys here are your double bonds, and your triple bonds are even more energetic and even rarer, so there are fewer of the triple bonds. And basically what this is saying to you is that if you want to break a hydrogen-hydrogen bond, so here's a hydrogen-hydrogen bond, and you want to break it so that it is now no longer together, then you're going to have to put in 436 kilojoules worth of energy for every mole that you do that. If instead you want to make a hydrogen-hydrogen bond, so you start with hydrogen-hydrogen and you end by making the bond over here, then that process releases energy, and it releases 436 kilojoules of energy. And basically what it then comes down to, lots of different ways that you can do this. You'll see it written different ways in different publications. But the short way of it is if you add up all of the bonds of the reactants and subtract from that all of the bonds that you're going to make in the products, then you're going to end up with the delta H of the reaction that is there. So let's check this guy out. Let's say that we looked at hydrogen plus oxygen going to water. So we're going to have to break this and this and this. All of those are bonds that we have to break. So the hydrogen-hydrogen bond we said was 436. So using that number, I'm going to have to put in 436, 436 twice, and then I'm going to have to break an oxygen double bond, which is over here at 498. So I'm going to have to put in all of that's there. So in order to break the bonds, I'm going to have to put in 436 and 436 and 498. So if I get out my calculator for this, I have to put in a total amount of energy, 436 twice and 498, 1370. So I have to put in 1370 kilojoules to break all of my bonds. And then what I'm going to do is I'm going to subtract here all of the energy I'm going to make over here by making these new bonds. So what are my new bonds that I am making? An OH bond, but there's going to be 4 of them. So 2 of them for that water molecule and 2 of them for that water molecule. So an OH bond is here at 464. So this is going to be then 464 plus 464 plus 464 plus 464 and 464 4 times. So that's 1856. So I am going to break my orange 1370 here, and then I am going to subtract from that my red 1856 over here. So my overall delta H of my reaction then is going to be 1370 minus the 1856. So I'm going to get negative 486 kilojoules out of it for this reaction to occur. So all you do is you figure out how much energy for the bonds that you have to break, subtract from that the energy, the bonds that you have to make out of it, and then you're in good shape. All right, here's some sample problems. What is the delta H for the synthesis of propane from propene and hydrogen gas? So again, they give you this Lewis dot structure, this overall reaction here, but they're not necessarily giving you the Lewis dot structure, although in this case they are. So all you got to do is add things up. It becomes kind of easy. It's just kind of tedious. So what have I got? I've got CH bonds. So my CH was 414 here. So every carbon-hydrogen bond is a 414. So that's a 414, and 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 that's a 414. So that looks like 1, 2, 3, 4, 5, 6. So I have 6 at 414 for my carbon-hydrogen bonds. That took care of him, 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 and him. Now it looks like I've got a carbon-carbon single bond and a carbon-carbon double bond here. Okay, let's look those up. Carbon-carbon single bond is 347, and carbon-carbon double bond over here is 611. So 347 and 611. So I come over here, and that's 347, that's how much he is, and then 611, that's how much he is. So that takes care of all of my bonds in that molecule. Now I got to destroy a hydrogen bond, this guy here. What did we say that was? 436, I believe. Yeah, 436. So that bond is a 436, so I have to add in another 436 here for him. Okay? And now I'm going to subtract from that everything over here that I am going to make. So what have I got? 414 for these guys here. So again, this is 414 and 414 and 414 and 414. You see the point? So this just gets a little tedious. If I add all of this up, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 at 414. And then I have this guy and this guy, which were my single bonds, which we said was 347, I believe. So that's 347 twice that is there to get him and him out of it. So consequently, 6 at 414 is that, and then a 347, and then a 611, and a 436. I got 3878 here to break, and then I'm going to subtract from that 8 at 414 with a couple of 347s here. That's going to be 4006. So my delta H for this process is 3878 minus the 4006, negative 128 for this process, assuming I've done my math right. All right, sample problem number 2 here. So a student wishes to determine the Ni bond energy in Ni3. According to the information below, don't use any other information. What is the experimentally determined value? Okay, so I'm not going to look back up at the chart for this problem because they're telling me only use the information that I see here. They're probably not going to give you this chart on the AP test unless they want you to do a particular problem, and then they're only going to give you the numbers that you need. So they're not going to give you access to this whole chart. So let's assume that you're on the AP test and you don't have the access to that chart that is there. You only get the access to what is given to you. So what do we know? So we know that the delta H of our reaction is going to be equal to the sum of the bonds of the reactants, the ones that you have to break, minus the sum of the bonds of the products, the ones that you get to make. So what is that going to be? Well, actually, they gave us delta H in this process. They told us it was positive 480. Okay, so I'm just going to go ahead and put that number in, positive 480. Now, what bonds do I have to break for my reactants? Well, let's see. I have a nitrogen and 3 iodines. So they kind of gave that to you. Oh, there it is, right there, a nitrogen and 3 iodines. And they told you that each iodine is 150. And they told you that the nitrogen is 950 that's there. So you're breaking a 950 and then 3 150s. That's what you have to do over here to break all of this stuff. Now over here for the products side, what are you doing? You are making 2 Ni3s. So if you are making 2 Ni3s, that means you have 1, 2, 3, 4, 5, 6 of these bonds, but they didn't tell you what it was, and that's the point of the problem. It says, what is the experimentally determined value for the bond energy of the Ni bond. I don't know what that bond energy is. So what have I got? This is X. So it's X, X, and X, and X, and X, and X here. So what I've essentially got here is minus 6X. I've got 6 of those bonds over there on the right-hand side that I don't know what they are. So at this point, it's just math. So I've got 480 is equal to, what is that, 450 and 950 is 1400. And that's going to be minus 6X. So 480 minus 1400 gets me negative 920 equals negative 6X. Divided by negative 6 gets me, each one of those bonds is 153 kilojoules for each of those bonds. Now let's cheat and see how we did. We got 153 according to our chart up here, and Ni bond is actually 159. So yeah, we're pretty close. We're in pretty good shape. So the experiment got us within a stone's throw of the chart answer at any rate. So again, all you're doing is taking the bonds of the reactants and subtracting the bonds of the products from them. All right, and that is